Detecting dangerous driving from mobile sensors. What if I told you that the solution to car crashes lies in your mobile phones? Nexar's vision is a world without collisions. Nexar collects driving data from a wide network of edge devices, dash cams and smartphones that detect events such as hard brakes, as we can see here. The data flow we were presented with starts with an edge device that detects such an event. Hard brake detected. Then ride segment data is created, where a video and the motion data is recorded of the segment of the ride that's surrounding the event. This is then uploaded to the cloud, where a human analyst manually labels it to see if there's dangerous driving. It gives it a label from 0 to 7, where 0 is nothing happened, and 7 is a car collision. But the company is only interested in events that are labeled 5 to 7. The business goal that we were presented with was reduce this cost of manual annotation and provide a real-time feed of annotated real events. Additionally, we were asked for interpretability, meaning a model that will be able to explain what the decision is based on. So we mapped this business problem to a data science problem, building a binary classifier for raw ride data. The negative label is nothing interesting happened, and the positive label is dangerous driving or collision. With the company, we also phrased the business goal in data science terms. The goal of reducing cost of human annotation can be met with a classifier that has a very high recall and moderate precision that is fed to the human analysts. Due to the very high recall, this classifier's detections miss only very few events. And due to the extreme class imbalance inherent in this problem, the resulting feed is much smaller in size than the original feed, hence the cost reduction. The combined classifier and human analyst that serve as an independent high-precision filter of the model detections give us what we want. The speed goal, near real-time annotation, can be achieved with a high-precision classifier. The high-precision classifier can be automated completely and giving real-time feed of almost all of them are real events. With that, I'll hand it to Rachel to discuss our data and approach.
Thank you, Meir. Hi, everybody. So what kind of data are we using? We are using sensors from our beloved mobile phone. And to be more specific, we are using the accelerometer, which measures the change in speed, gyroscope, which measures the rotation of the device, magnetometer, which measures the orientation of the device, and GPS, which gives us the location, speed, and course. We also have the camera, but we didn't use it in our project. Each sample is basically 4 CSV files from 4 different sensors that we combine into one sample, and is labeled as dangerous or not dangerous. Now, as Meir said before, Nexar is giving scores from 1 till 7, while 1 is not dangerous at all, and 7 is already a collision. From our discussions with Nexar, we realized that the main task is to catch the dangerous ride, so we simplified our problem into a binary classification task. So now let's take a look on how our data looks like. So this is an accelerometer data of 2 rides. One is dangerous and one is not. Which one do you think is dangerous, left or right? Okay, so majority was wrong. This is a dangerous one, and we're going to show you a video saying why is it dangerous. And this is probably due to a user dropping his phone. Now, this is a map of New York based on our GPS data. The red dots are dangerous rides, and the blue dots are non-dangerous rides. We actually built that map because we wanted to see if there are certain locations with more dangerous rides. But as you can see, it's very mixed. We didn't have any conclusion. But what we did learn, if we zoom out, is that majority of the rides are inside very big cities like New York, San Francisco, Chicago. And if we zoom in on Chicago, you learn that they are the safest drivers, all blue. Okay, so now we're going to talk about our approach to the problem. We started with a base model and handcrafted feature, starting with only accelerometer because we feel it's the most intuitive one, yes, right? Change in speed can tell you a lot about a dangerous ride. Then we added gyroscope, GPS, and data augmentation to see if it improved results. And then we took the deep learning approach, mainly playing with ResNet, and gradually adding the rest of the sensors. Some of the data challenges that we had. So different sampling frequency. Here you see the accelerometer and GPS. Accelerometer is measured 50 times a second, GPS is measured once a second, and we had to deal with that. Different axis orientation. For the same situation, when a user is holding his phone in a portrait mode, or the other way, it sweeps the X and Y axis. And of course, we had limited label data, and this affected our work. Some of our feature engineering that we did, very standard time series feature engineering. We also took a more complex approach, using TS Fresh and adding thousands of features. And this is a nice example of the data augmentation we did with the GPS. If you take a look at the course, when it is changing dramatically, then we know there was a turnover there. Okay, so this is a summary of the experiments we made with the base model. Now, it looks like a very good start, and we have an Nexar representative here that was very skeptical. Hi, Ellie. So they gave us additional validation data to see if we get consistent result, and we did. So let's zoom in on the best performing base model, okay? We are going to look at the precision recall curve of this model, the red one, and there we marked the two business goals. Okay, the first one is the one with very high precision, which means that if we classify a ride as dangerous one, it's most likely to be dangerous. And for Nexar, it means near real-time detection. The other one with very high recall means that we managed to catch majority of the dangerous rides. And for Nexar, it means reducing cost of human annotation. Now, the red curves tell us that we didn't achieve our goals yet. So I'm going to let Andrey explain you and walk you through the process of how we achieved our goals.
Hi, everyone. I'm Andrey, and I will discuss to you the deep learning approach we took to solve this problem. So at this point, we had a pretty good grasp of our data, what to do with it, and as you saw, we had pretty decent results, but unfortunately, we weren't quite there yet. So the paper that I'm referring to here actually laid the groundworks for the architectural decisions for a model we're going to build. This is our first iteration of our model. It has two key factors. One, we use full convolutions, and it means that we keep the input size the same throughout as we go deeper into the network. Unlike the regular convolution that some of you used to, we go smaller in size while increasing the filter. Additionally, we have the global average pooling layer at the end. Not only it drastically reduces the parameter size of the model, thus helps combat overfitting, but it also has this very special property that I will discuss with you later on. Next, of course, we got deeper. So instead of the regular layers, we moved to residual blocks. Now, this is not the ResNet, but a network that uses residual connections. And we've added the gyroscope data now. Now we have to add the GPS. Now remember, we told you it has different frequencies. So how do we add this data to the same network? So we actually had to add it as an additional input to the model with a smaller residual block and concatenate it at the end of the network. Now, how we can improve this even better? We've used all our raw features up until now, so what we can improve here? Remember the handcrafted features we used at the beginning for the base models? So we actually introduced them as an additional input feature, again in this model. And here we have, at the end of the network, actually a dense representation of the handcrafted features and the raw features we got from our convolutions. Now, the dangerous ride that Rachel showed you, now this is, take a look at how it looks like in the real video. On top, we can see the accelerometer data. You have the GPS. This is, by the way, Rishon LeZion, if you notice it. And watch what happens when we get closer to the interesting event. Whoops. So, no collision happened, but a really dangerous maneuver occurred on the road. So, this is actually what you saw. Now let's take a look at what the network saw. This is a sliding window of the same video that you just watched, and as it gets more information from the ride that you just saw, we can see it's starting to make a higher probability decision on the event that has happened. And as it has much more information, it can actually produce the correct classification. Now, let's talk a little bit about class activation maps. Remember the global average pooling layer that I told you about? This is Luna, by the way, my dog. So there is this special property of global average pooling layers that you can actually, with a special technique, mark the specific pixels that will tell you where the model is looking at when it's making the correct classification. So we took this novel approach of actually using the same procedure on time series data. I don't know if it's seen here, but take a look what is happening. It actually making a pretty high decision on the event. This is the same from the video that you saw. And it captured that the event actually happened in the middle. But now watch what happens when we run the same procedure through our best ResNet. This is blue, by the way. It can actually ignore irrelevant information even better, as you can see in this graph, and thus making a much higher probability decision. So I will let Meir go over with you with the rest of the results.
So we started with the accelerometer. We gradually added more features, more sensors. We processed raw data with a deep network. We added engineered features. We added application-specific engineered features, such as the turn detector. And we reached our performance. So, did we make it? Let's see. We beat the speed target, and we beat the cost target. We beat both preset business targets given to us. Okay, the business impact to Nexar is the cost. The cost, labeling of the cost drops 80% due to the class imbalance. And the speed, we give a near real-time quality feed of almost all interesting events. As for the interpretability, we innovatively are using class activation maps on time series and additional features to create the desired interpretability. Future work is also clear. We did not use yet the video. We add the video to the model, the raw data, or features that can be derived from the video, such as lane information. Now, we can add more hand-engineered features from clustering model errors into the framework previously introduced. So with that, we'd like to thank our great mentor, Dr. Glib Ivaschkevich, Nexar's VP of Research, Dr. Eli Brosh, who's sitting right here, and Nexar Data Ninja, Tomer Achrak, for hosting and supporting us throughout this project. Thank you very much.